Today we're going to start looking at how we use our equations, using our calculators, and trying to make sense of the equations using the data that we have. Our directions say, recently you read about the walkathon and considered three possible pledge plans. If A represents the dollars owed and D represents the number of miles walked, we can express these plans with the equations below. Leanne's plan, A equals D. Gilbert's plan, A equals 2D. And Anna's plan, A equals 5 plus 0.5D. I want to go ahead and talk about just briefly the independent and dependent variable. Now on something like Leanne's plan, it's difficult really to tell what the independent and dependent variable is, except I will tell you that in general, and there are exceptions, your dependent variable is going to be on the left side. So the dependent variable is A, the independent variable is D. A stands for the money raised, and D stands for the number of miles walked. Now it's a little easier to see in Gilbert's plan because here we have D is inside the equation and A is on the left. And the left is where you normally see, it doesn't have to be there, but normally where you see the dependent variable. Here's the dependent variable. The independent variable is going to be this D right here. I want you to notice we have a constant, which is a starting point. This is a constant. And we have a coefficient. We have a coefficient here with 2 and no constant, and we do not have a visible coefficient here. Kind of an invisible coefficient would be 1. Well, we're going to look at using the graphing calculator, and what we'll be doing is we'll figure out what does any of the equations mean, but what does Leanne's equations mean? And if we use Gilbert's plan, how much will a sponsor owe a student who walks 5 miles? Using Anna's plan, how far will a student have to walk to earn $17? So here we're going to see if we have an input of 5, what will the output be? And on this one, if we have an output of $17, what does our input have to be? In other words, how many miles? So here we're going to look at point 412, and Anna's equation was, let me scroll back up so you can see it. Anna's equation was a starting donation of $5 plus 50 cents per mile. So if we had point 1412, this is the x value, so it is independent. Notice our independent variable is right here. That means if we walk 14 miles, we make $12. See? If we walk 14 miles, we make $12. All right. It says for a sponsor to owe $17 under Anna's pledge plan, how many miles would the student have to walk? Now let's look and see how we can use our calculators. Here we have our dependent variable is equal to an initial deposit of $5 plus 50 cents per mile. I'm going to rewrite this. Our dependent is usually a y, the initial value plus 50 cents per mile. And whenever we have that per or each, you're usually looking at whatever follows it is going to be your independent variable. So on your calculators, turn it on, and I want you to come up here to this top left button, the y equals. Let me see. I think I'm going to have to restart this. Yeah, I do have to restart. Bear with me for just a moment. So I'm going to come up here to this. Let me close that out back. Oh, no, cancel. All right, I'm just going to minimize that. I'm going to come up here to my y equals. And here I have my y equals. And what I need to do, let me get off of that, is I'm going to fill in the rest of my equation right here. So I'm going to put in 5 plus 0.5x. And what I'm looking for is, and I'm going to hit second, this button here, graph. Your colors may look different. Is I'm looking in this y1 column, that's my y values, for the number 17. And the reason I'm looking for that is our question asks us if we're going to make $17, how many miles would the student have to walk? Remember, the x is in place of the miles, the y is in place of the dollars. So I can look here and I see 17 y dollars equals 24 miles. So my answer would be 24 miles. All right. It's going down. Chuck is trying to answer a question about Anna's pledge. He writes A equals 5 plus 0.0528 or times 28. Well, what question is he trying to answer? Well, we look at what is it that we have that's a variable still. We have A, which stands for the dollars. So I could say, how much money would she earn if she walked, and we're given the x value, 28 miles. Daniel is trying to answer a question about Anna's pledge. He writes 46 equals, and then the rest of it, but we don't know what that is. So what question is he trying to answer? Well, this is going to be, how many miles must she walk to raise $46? Because we're given the amount raised and we're looking for the miles needed to walk. Now let's turn your paper over and we're going to go back and look at our calculator again. So what I want you to do is go back to the y equals. I see we're going to have to go through this again. see if I can. We'll go back to our y equals. Seem to be having a little bit of a technical difficulty here. Let me close that out, open up a new file. Well, and thank you for bearing with me. Let me bring my calculator back into the screen area. So, cancel. Oh, goodness. Well, what I want you to do, while I am bringing my calculator back up, I would like for you to go ahead and find your y equals and put in the 3x. And thank you for bearing with me. I'm going to get this situated here. So what I'm going to do, I'm going to my y equals. I'm putting in my 3 and my x, which is right next to the alpha. Do not use this multiply sign. That is not an x. And do not try to put in the alpha characters down here. In this case, x is a variable, and we're going to use the variable button. What I want you to do is I want you to get into a habit of looking at graphs and filling them out in a certain way. And the way I would like you to do it is, rid of that, is we're going to put in -2, -1, 0, 1, and 2. Then we're going to look at our thing, and when x is -2, y is -6, and I'm just copying here. When x is -1, y is -3, and it's 0, 0, 1, 3, and 2, 6. So now what I want you to do is I want you to plot those points. I'll try to use a different color here. So I have -2, so I'm going to go left 2, then down 6. 1, 2, 3, 4, 5, 6. And then I have -1, -3, 0, 0, 1, 3, and 2, 6. Come on. There we go. Now, when we connect these, and my lines are not usually very straight, but we need to connect it all the way across, and we're going to put arrows on both sides. If you don't go end to end, and if you don't put arrows, then it is not correct. So here it says make a table and a graph to determine whether or not the equation represents a linear function. Explain your answer. Well, now if I could draw nice and straight, that would be a nice straight line. And it is straight. There are no two places, or no place where there are two x values, so it passes my vertical line test. This does check out. It is linear. So what we'll do is we'll go to number 6. Oh my goodness, look at all the mess I have on my screen here. Not sure where all that came from. We'll get rid of it. And I see we lost the calculator again. So I think I'm an expert now. I will open a new one. We're going to say no. We're going to get that going. And so we're good. We're back. Let me bring that back into view for you. I'm going to put in y equals 3 to the power of x. So I go to my y equals. I'm going to put in my 3. To raise something to the power, you have this little caret button. So that's to the power of. And then we're going to put in our variable x. And then we're going to go to second graph. And we're going to look at our table. I want to see -1, or -2, -1, 0, 1, and 2. So here I'll come over here. And we'll put in -2, negative 1, 0, 1, and 2. Our y values are 0.111, 0.333, and then it's 1, 3, and 9. Let me get a different color for this one just so we can see it. So at negative 2, it is 0.111, so it's not quite at the 0, so I'm just going to put that like right there. Here it's about a third of the way up. There we go. Here it's 1. 1 is 3. And 2 is 9. That'd be 6. That'd be like, that would be something like right way up here. And so our line literally will be going like this. Is that a nice straight line? No. So it is not linear. And anytime you see this construction, that is called exponential. Exponential. It's time to start learning those. That is exponential. All right. Here we have 2x squared. So I'm going back to my y equals. I'm going to clear that out. I'm going to put it in just as it's written. 2x. And then if it's squared, because we do that a lot, you can use this square button right here. So you see I have 2x squared. 2x squared over here. I'm going to hit second graph so I can see my table. I'm starting at negative 2. So I have negative 2, negative 1, 0, 1, and 2. And I copy down my values from the y column. On the right, 8, 2, 0, 2, 8. And then I can plot those. So I'm at negative 2, 1, 2, 3, 4, 5, 6, 7, 8. It would be right about there. Negative 1 would be 2. Come on. 0, 0. Then it would be 1, 2. And 2, 8. Come on. There we go. So now, this again is not a straight line. So it is not linear. This is actually what we call a quadratic. And it's quadratic, we can tell because it has this U-shaped graph. So number 8. For a graph to be linear, it must, and can you get it? Hopefully you can. It must be a straight line. Oh goodness. And I'm just going to put here, must not have exponents. All right, circle the linear equation. Well, does this have any exponents? Okay, it does not have any exponents. So this would be linear. This does not have any exponents. This does not have any exponents. And this, well, I better not do that, because then it's tough to see what's going on. That is not, because it has an exponent there. All right, for a table to be linear, I want to scroll back up here for just a moment, and I want you to notice that I'm looking at this, and this goes up by 1 there, by 1 there, by 1 there, by 1 there. It doesn't have to always go up by 1, but I want you to see as these go up by the same amount, this from -6 you have to add 3 to get there. From -3 to get to 0 you have to add 3. If you have to go there, you have to add 3. From 0 to get to 3. From 3 to 6 you add 3. So we notice that everything is going up at the same rate. If these are the same on the left, then these should be on the same on the right. And our answer is, for a table to be linear, it must show the same rate. Now if we look at a non-example, this goes up by 1, up by 1, up by 1, up by 1. So it's all the same on the left. From here, it goes up 0.222. From here, it's going up 0.66 there. From here, it goes up 2. From there, it goes up 6. So these are all different rates. Okay? If we look, we went up 1, up 1, up 1, up 1. This, it went down 6. It went down 2. Oh, now we're adding 2. Now we're adding 6. Well, here we're going down and then we're going up. So it is not going up at the same rate. It is not going down at the same rate. In fact, it is doing both. So you must show the same rate on the table.